Hello everyone, my name is Ulal Wenam and today I will give a brief introduction to photonics. So for the course content, first I will start with ray optics and then we'll move on to wave optics. After that we'll go on to electromagnetic optics and finally we'll go to the quantum optics. So first let's start with the ray optics. So in ray optics we have two laws. First is the law of reflection and second is the law of refraction. And as we already know, law of reflection says that the angle of incidence is equal to the angle of reflection. But in the case of the law of refraction, it says that when light travels from one medium to another medium, the light bends towards the normal or away from the normal depending upon from which medium it is traveling from. So when light travels from a rarer medium to a denser medium, the light actually bends towards the normal. But when it travels from a denser medium to the rarer medium, the light it bends away from the normal. And for the law of refraction, we actually have a law that is called as the Snell's law, and it says that the product of the refractive index of the medium 1 into the sine of the angle of incidence is equal to the product of the refractive index of the second medium into the sine of the angle of refraction. So we have the Snell's law, and going according to this, we actually have another concept. That is the critical angle. So what is critical angle? Critical angle is nothing but it is the angle of incidence for which the angle of refraction is 90 degrees given the condition that the light travels from a denser medium to a rarer medium. So in this like Snell's law, we are going to find out the critical angle. So we have n1 into sine of critical angle theta c equal to n2 into sine of 90 degree, because the angle of refraction is 90 degree. So it implies that n1 sine of theta c equal to n2. So if you want to find out the sine of theta c equal to n2 by n1, which make it equation number 1, and then we have the critical angle theta c equal to sine inverse of n2 by n1. Now we have the critical angle theta c equal to sine inverse of n2 by n1. So another question comes into mind, that is, why do light bend when it goes from one medium to another medium? And in order to answer this question, there are multiple theories and propositions, and one of the most familiar one is the soldier marching theory. So we have this diagram, and then we have this swarm, and then we have the field. And if we imagine a front line of soldier that is marching from the field to this swarm, and as we can see from the figure, the bottom soldier is actually closer to the swarm than the top soldier. So when this front line of soldier move from the field to the swarm, the bottom soldier will be moving a smaller distance as compared to the top soldier. So the direction of marching when it goes from the field to the swarm will change, and we actually use this concept to say why the light bends when it goes from one medium to another medium. So this is just a theory, but in the actuality, so why does it bend? In order to solve this, we have to go to the electromagnetic optics, and we'll discuss it further in the next 10-20 minutes. So in order to give a brief idea of how it works, is that we know that light is an electromagnetic wave, and it has the electric field and the magnetic field. So it has to do with the interaction of the electric field with the charges with the charges in the material. So let's assume that the light is going from here to another medium, and let's suppose glass. Then the electric field component of the light actually causes the charges inside the glass to align themselves, creating a net charge, and this net charge actually oppose the electric field component of the light, which causes changes in the direction of propagation of the light. And if we go down this concept, we will find the effects such as the Kurz effect, where we have external magnetic field, So this external magnetic field changes the extent of the alignment of these internal charges, creating changes in the refractive index. So after this, we'll go into fiber optics, and then we'll go into the limitation of ray optics, and then we'll go into wave optics. So what are optical fibers? Optical fibers are transmitting medium that propagate light from one end to another end. And here we have a rough figure of an optical fiber. And it consists of two parts. One is the core, that is the inside part, and then we have the cladding. And how does it propagate light? Well, the light coming out from the outside gets coupled onto the optical fiber, and it propagates through the process of the critical refraction. And for critical refraction, we know that the we know that light should travel from a denser medium to a rarer medium, and from that we have this the refractive index of the core N1 is greater than the refractive index of the cladding, that is N2. And in context to this, we actually have one more, that is we have actually one more concept, that is the concept of the acceptance angle, that is the maximum angle up until which it is a maximum angle up to which light gets coupled onto the optical fiber. And further we actually have one more expression, that is so for this expression we are going to use Snell's law, that is so we have refractive index of the surrounding air, and we are going to represent it with n naught sine of the accident angle theta a, it is equal to n1 sine of we have theta c bar. So theta c bar is just the angle of refraction. So we are going to imply for n naught we are just going to represent with 1, and we are just going to remove sine theta a, it is equal to n1. And for this for the concept of the acceptance angle, for the maximum angle, we know that the refractive ray should actually make critical angle inside the core. So for this theta c bar, we are going to represent it with sine of, and we know this sine of 90 degree minus critical angle theta c, and we can clearly see from this simple diagram. So we have sine of the critical accident angle, it is equal to n1, and since it's sine, it should be represented with cos of theta c. So how do we further? So we know that the sine of the critical angle theta c equal to n2 by n1 from the previous from Snell's law, for that is for the critical angle. And so let's represent it with a Pythagorean triangle. So in this triangle we have sine of theta c. So we have theta c, we have, and for the perpendicular we have n2 and hypotenuse n1. So the base will be root over n1 square minus n2 square. So if we represent here, we have n1 into root over, for since the cos, n1 square minus n2 square by n1, and then we will cut this, and then we are going to have sine of theta c is equal to root over n1 square minus n2 square. And so we have the sine of the acceptance angle, it is equal to root over n1 square minus n2 square, and we also call it as a numerical aperture. So this root over n1 square minus n2 square is also known as the numerical aperture. So in the context of optical fiber, depending upon the diameter, optical fibers can be divided into single mode fiber and multi-mode fiber. So what is the difference between the single mode fiber and the multi-mode fiber? In the case of single mode fiber, the diameter is small enough such that the light ray that gets coupled onto the core, they actually travel closely compared to one another, and also they don't interfere with one another, such that the resultant output we get a single speckle pattern, speckle pattern in which the intensity graph looks that of a sinusoidal wave. But in the case of the multimode fiber, the diameter is large enough that it can support multiple paths. So when it can support multiple paths, such that at the output we have multiple speckle pattern, and this speckle pattern is because of the light rays interfering with one another. And also we have this concept. So when light travels at different parts inside the core, it takes different time for it to reach the output. And in case of communication, it causes a problem. It causes a latency problem. So in order to solve this, we have another variation of this. And for this one, we call it the step index fiber, where the refractive index remains the same for the core and the clarity. But in order to solve this problem, we have another one that is known as the graded index fiber, where the refractive index changes when it moves from the center towards the side. So it actually decreases. So in such varying refractive index, when light travels forever, for multiple parts, when you reach the output, they will be reaching at the same time. So we have this type, and for the next one, we'll be looking how do we classify the modes. So in this concept, we also have one more concept, that is the V number. V number is just another parameter that is used to identify the number of modes. So V is equal to 2 pi into radius by lambda, and then we have the numerical aperture. So this is the formula for the V number, and then we find out the number of modes, that is the number of speckle pattern, m equal to 4v square by pi square plus 2. So next we'll be looking at the the number of modes and the speckle pattern. For the last topic, we will be focusing on the modes and how do we name them. So all the modes follow a particular naming pattern, that is LP, MN. M usually represent the radial, while the N represent the azimuth zero. But for our own basic understanding, we'll be using some just some simple, like how do we name them. So the first one is actually named LP01, while the second one is named LP11. So how do we name this? So what this 0 signifies, and what does the 1 signify? So let's name the third one, and then we'll understand. So if I draw a line from the top, and it passes right through the center, and it passes two of the modes, so how many of such line can I draw? So for this one, I can draw the one vertical line and one horizontal line. So these are two lines that I can draw. So I'll write LP2, and for the N. So if I take this point, and then if I trace out a radial line, and if I rotate this radial line, so what is the maximum number of speckle pattern that I'm going to find out that this line is going to meet when I rotate it 360 degree only at a single instant. So when this radial line traces out, it is going to meet it is only going to meet a maximum of one pattern at a time. So it becomes LP2 1. So for this one, how many of this? So let's name for this one the fifth one, that is LP. We have 1, 2, and then we have 3. So LP3, and we'll take the radial line and we'll rotate it. Maximum of one speckle pattern, I mean. So LP31. And for this one, we are going to draw this one. So this will be LP0, because for this one we are tracing out a complete speckle pattern. For the one, it is never complete. So LP0, and then if I take one radial line, and if I trace it around 360 degree, at a maximum I'm going to make two speckle patterns. So this is the first speckle pattern, and this is the second speckle pattern. So LP0, 2. And for this one, we have to draw one line. So it is LP0, and then when it rotates at the radial line at a single instant, the number of modes will be 1. So when it rotates, so it will be LP01. For this one, this will be LP1, and when it rotates, so when I take a radial line and when it rotates at a maximum at an instant, the number of modes it meets will be 1. So we have the LP1. Now let's get into wave optics. So why do we require wave optics? Well, there are some phenomena such as diffraction which can't be explained with ray optics. So ray optics actually fails when the considering obstacle, when the size of the obstacle is near to its wavelength. So in such a condition, ray optics usually fail. And in order to solve this problem, we will be considering like light as a wave. So, and in order to go into the diffraction pattern, or in order to go into the wave optics, we need to know what is diffraction. So what is diffraction? Well, diffraction is a phenomena of bending of light when light encounters obstacle that is close to its wavelength. And also we need to know another concept, that is the Huygens principle. So what does Huygens principle states? Well, Huygens principle says that every point on a wavefront is the source of another spherical wavelength. And with these two concepts, we will be going on to the single slit diffraction. So what is a so how does a single slit the experiment work? Well, in single slit diffraction, a wavelet, okay, no, not a wavelet, a wavefront. So this one will be the wavefront. With the wavefront encounters a single narrow slit or aperture. So this gap is the aperture, and this like aperture causes the wave to spread and interfere with itself. That is when we have a little bit gap, it will have multiple spherical wavefront because of diffraction, and this multiple wavefront, they will interfere with one another. And when we say this interfere, we are talking about the constructive interference or the destructive interference. That is, the intensity adds up, or that they cancel out each other. And after this interference, that they will give it will have a pattern that is known as the diffraction pattern. And in this diffraction pattern, we will be having a central maxima, and they will having secondary maxima, with the central maxima having the highest intensity. And then we will have the secondary maxima, which will have a lower intensity, and then it will spread out to the sides. So this is a single slit diffraction, and the intensity pattern usually resembles that of a sinusoidal wave. And then we'll go into the double slit experiment. Okay, and before that, we will be going into a single simple formula. There is the sine of the angle theta is equal to m lambda by a. So what is this angle theta that we need to find? So we have this central maxima, and then we have the other maxima as well. So the other maxima are given order, like the first maxima that is closest to the central maxima is given order 1, and then the second one is order 2, and then the third one is the order 3. So the angle made from the aperture itself to the first maxima or the second maxima, that we represented with theta m. So this theta, so how do we find out this theta? So the formula is given by sine theta is equal to m lambda by a, where m is the order of the bright spot that we want to find out, and a is the width of the aperture. And so theta is the angle of diffraction, and m is an integer that represent the order of the diffraction, and lambda, and as we know, lambda is the wavelength of the light, and then we have a, that is the width of the slit. And now we'll go into the double slit experiment. So in double slit diffraction, so it is built upon this single slit experiment. And just as in the single slit diffraction, where a wave passes through a narrow aperture and create a distinctive diffraction pattern, it usually use the same concept. So in this setup, there are two closely spaced slit which acts as source of secondary waves, and these waves subsequently interfere with one another. So the secondary waves that will be coming out of the S1 will interfere with the secondary wavelets that will be coming out of the they will be coming out of the aperture S2, and this interference pattern will give out the interference pattern onto the screen. And in this interference pattern, all of the maxima will usually have the same intensity. That is, but when look closely, all of them will have the same intensity. But when we increase the sample cycle, increase the number of sample, or with a large number of reading, then we kind of realize that it usually follow the diffraction pattern of the single slit diffraction, where the central maxima is composed of multiple where the central maxima is composed of multiple maxima. So after this we will go on to the um, like multi-slit diffraction. So what is a multi-slit diffraction experiment? Well, instead of having two slits, we'll be having multiple slits. So when we have multiple slits, the intensity of the peak will greatly be enhanced. That is, the intensity will be directly proportional to m squared, where m is the number of slits being introduced. And so the actual formula will be I equal to I naught m square, where I naught is the original intensity that is coming through the slit. And also in this multi-slit diffraction, there will also be other secondary maxima, and the number of secondary maxima that is going to be formed is equal to m minus 2, where m is the number of slits. Now let's get into two interesting topic, that is the interferometer. And first we'll start with the Michelson's interferometer. So what is a Michelson's interferometer? Well, Michelson's interferometer is an optical instrument that is used to measure the wavelength of the light and also test the optical properties of some other component and also perform experiment. And what does it compose of? Well, it composed of multiple parts, and the first part we are going to discuss is the beam splitter. So what does the beam splitter do? Well, the incoming light is directed towards the beam splitter, that is from the laser, and then this beam splitter will reflect a portion of the incident light, okay, and will reflect a portion of the incident light, and then it will transmit the rays to the another mirror. And as I've said, we have two mirror, okay. So the transmitted and reflected light beams from the beam splitter travel to two separate mirrors, that is mirror 1 and mirror 2, and it is positioned at precisely equal distance, okay, an equal distance from the beam splitter, and these two mirrors reflect the light beams back towards the beam splitter. And it is very necessary because they are going to recombine. Well, the two reflected beams recombine at the beam splitter itself, and then depending upon the path difference between the two beams, that is from mirror 1 and mirror 2, they may interfere, that is constructively or destructively. And then we have the detector or the screen. And when the path difference of the two arms of the interferometer are exactly equal, the two beams coming from mirror 1 and mirror 2, they recombine and they don't have any phase difference, and leads to constructive interference at the detector, okay, and that result in a bright fringe, and when one of the mirror, okay, this is concept, when one of the mirror is displaced slightly, it introduce a path difference between the two beams, and depending upon the path difference, the recombining beams may interfere either constructively or destructively, leading to the appearances of dark and bright fringes respectively. And for this we actually have a simple formula, that is the path that is the distance difference between this L1 and L2, and represented by D. It is equal to n into lambda by 2. And now let's go into the Mach-Zehnder interferometer. Well, in Mach-Zehnder interferometer, it is also a similar optical device, and it is used to measure small changes in the refractive index of a medium, that is the sample. So in here we have the light source, here we will have the laser, and it will give out a coherent light source, and then it will pass through a beam splitter. So the incoming light beam is divided into two separate beams, and the two separate beams are usually are the reference, and the two separated beam will follow two parts. One will be the reference and one will be the sample part. So the two split beams split beam will follow a different part, and one of them is and I've said earlier, and one of them is the reference beam, and another is the sample part. So this one is the reference beam, and this one will be the sample part. and in between the and in the sample part we may introduce some like glass slab or any or some other sample to introduce a phase difference. And after that these two light traveling in the reference and in the sample part, they recombine, and then we have the interference pattern. And the third one will be the Newton's ring. So what is a Newton's ring? Well, Newton rings refer to a phenomena of fringes observed when a plano-convex lens. So this is a plano-convex lens, and this is placed on top of a flat glass surface. And when it is placed on this flat glass surface, an air gap will be formed. So and how does it work is that when light reflects from the top and the bottom surface of the air gap. Here we have the air gap. So when light reflects from the top, again top and bottom of the air gap, this reflected light will interfere with one another and will form the Newton's ring. And the ring pattern is due to the variation in the thickness of the air waves. That is, since it is a plano-convex lens and then we are putting on top of a glass surface, there will be variation in the air gap and it will be smooth. So as a result, we'll have a ring pattern. And this ring pattern will decreases as we move away from the center. That is the spacing between the rings itself. So the spacing between the rings will decrease as we move away from the center, because here the air gap is actually increasing exponentially. And this Newton ring, they are often used in optical experiment that is used to determine the wavelength of the light or to assess the flatness of the optical surface. We have come to the end of the wave optics, and now we'll be going on to the electromagnetic optics. But before that, let's talk something about the wave optics. So wave optics offers something that ray optics cannot give. Like for example, the phenomena such as interference and diffraction, and which involve phases. But in spite of its success, that is the wave optics, it has its own shortcoming like the ray optics, and it is unable uh, to explain some of the phenomena such as the division of light at the beam splitter. That is the fraction of light reflected and transmitted. Um, so this fraction turns out to be dependent on the polarization of the incident light. So it means that light should be treated as a vector. So using this concept in mind, let's move on to the electromagnetic optics. So what is electromagnetic optics? Well, electromagnetic optics is a vector. It is a vector theory that comprises of an electric field and a magnetic field that varies with time and space. And the most important part of the electromagnetic optics is that it is governed by the Maxwell's equation. So here we have the Maxwell equation. It has now let's get into a polarizer. So what are polarizers? Well, a polarizer is an optical device or material that selectively transmits light waves with a specific polarization orientation, and at the same time block or attenuate light waves with with other polarization. We know that light waves are electromagnetic waves, right? That oscillate in various directions perpendicular to the direction of its propagation. And so polarization and so polarization actually refers to this orientation of this oscillation. And this polarizer, they work, and how they work is that they work by allowing light waves with a certain polarization direction to pass through them, and at the same time filtering out or reducing the intensity of light waves with different polarization. And now after this polarizer will go into the Manos law. Okay. And we have the Manos law. So what does the Manos law states? Well, Manos law, and also known as the Manos principle or the Manos theorem, describes the intensity of polarized light after it passed through an initial linear polarizer. So after it passed through a polarizer, the Miller's law states the Miller's law gives information about the intensity, and in it and about this intensity, and it quantify how the intensity of light is reduced as is reduced and how is it reduced, and it is reduced as a function of the angle between the initial polarization direction of the light and the axis of polarizer. And the axis of polarizer means the axis where the where maximum of the light that matches this axis of polarization passes through, while blocking others that does not match this axis of polarizer. And this Miller's law formula is given by I naught is equal to I naught cos square theta, where I naught where I is the intensity of light transmitted through the polarizer at an angle theta with respect to the initial polarization direction, and I naught is the initial intensity of the light before passing through the polarizer, and theta is the angle between the initial polarization direction of the light and the transmission axis of the polarizer. And after this, now we'll move on to the half wave plate and the quarter wave plate, and they are also known as the retarders. So first we'll go to the half wave plate. So what is a half wave plate? Well, a half wave plate is an optical device, okay, that introduce a phase difference of 180-degree between the two orthogonal polarization components of the incident light. So in other words, it changes the polarization direction of linearly polarized light while keeping its intensity constant. So when linearly polarized light passes through a half-wave plate, its polarization direction is rotated by an angle theta, and and where theta is determined by, and this theta is determined by the orientation of the half-wave plate. So this half-wave plate actually contains known as the fast axis, and then we have the slow axis. So so when this incoming light has a polarization that matches with the fast axis, then nothing happens. It passes through this half-wave plate easily. But when it comes in contact with the slow axis, it lags behind. So we have this half-wave plate, and we have polarized light that is coming at a particular angle, not directly onto the slow axis or the fast axis, but at a slanting angle. So this coming polarized light, it gets resolved, it resolved that is mathematically it gets resolved to these two axes, the slow axis and the fast axis. So so the light, so the portion of the polarized light, they goes to the fast axis, nothing happened, they don't have any phase lag or anything. But the one that goes through the slow axis, they got lag. So because of this, what happens is that the initial axis of polarization gets shifted by by an angle to theta, where theta uh, is the angle between the fast axis and the incoming axis of polarization of the light. And now we'll move on to the water wavelength. So okay, so this is for the half wave plate, and I have mentioned before it says about 2 theta and everything. Now let's move on to the quarter wave plate. So what is it like quarter wave plate? Well, a quarter wave plate is an optical device that introduces a phase difference of 90-degree, or 1/4 of a wavelength, between the two orthogonal polarization components of incident light. And this quarter wave plate is is different from the half wave plate,
It is unlike a half wave plate, a quarter wave plate does not change the polarization direction of linearly polarized light, but rather converts it into circularly polarized light. That is, the direction of rotation of the resulting circular polarized light, that is either it is uh, right circularly polarized or left circularly polarized, depends on the orientation of the quarter wave plate. And this quarter wave plate are often used to convert linear polarized light into circularly polarized light or vice versa. So how does this quarter wave plate works? Well, we have this quarter wave plate, and then it will have two axes, just like the half wave plate. It will have the fast axis, and then we have the slow axis. The fast axis is also called as the optical axis. So when light falls at an angle, like say theta, onto the at an when light with the polarization falls onto the quarter wave plate, inclining, having an angle difference theta with respect to the fast axis, then the orthogonal part of this incoming light that passes through the slow axis will get a phase leg, will get a phase leg of lambda by 4, or we can say 90 degree. So uh, the part of the light that passes through the slow axis will get lag by 90 degree, while the one that passes right through the fast axis will not get phase lag. So when it gets so after it passes through the plane polarized light, it either turns into circular polarized light or elliptical polarized light. And also, since it lacks one of the component by 90 degree, so when we input this quarter wave plate by a left circularly polarized, it turns into oh no so I'm sorry about that. Actually, it is so in this okay, sorry, I'm sorry about that. So it is actually the how we have it. So when a like circularly polarized light, usually in the orientation of either left or right of the for the sake of the conversation, let's take a right circularly polarized. So when a right circularly polarized light falls onto the half wave plate, it lacks one of the component by phase angle 180 degree. So after it passes through the half wave plate, the right circularly polarized light will turn into the left circularly polarized, and we will discuss why, like, what do we mean by left circularly polarized and right circularly polarized. So let's have this concept. So um, this light actually have two components, and when it comes to this orientation, we will be considering two electrical component, one in the x direction and one will be in the y direction. and this too will be depending upon the uh, depending upon either it passes to the half wavelength or quarter wavelength, it will have a phase difference. So the resultant of the instantaneous value of the y-axis component and the of the x-axis component and the y-axis component will be the resultant, and this resultant will actually so when this electromagnetic wave propagates, this resultant will trace on a particular pattern. So when this resultant of the x-axis and the y-axis, if it rotates in the anti-clockwise direction, as it propagates through, then we call it as the left circularly polarized, and if it rotates in the clockwise direction, then we call it as the right circularly polarized. Now let's get into quantum optics. So according to quantum optics, what is a photon? So from a quantum perspective, light consists of particles called photons, and this photon carries electromagnetic energy and momentum, as well as intrinsic angular momentum or spin associated with its polarization property. It can also carry orbital angular momentum. So why do we require this quantum optics? Well, it can explain some of the very simple phenomena such as emission, absorption, etc. So now let's get into absorption. So we know that light is a packet of energy called photon. Light consists of packet of energy called photons. So when we have an electron that is in the lower energy state, and when this packet of energy called a and when this packet of energy called photon interact or hits or interacts with this electron at the lower energy level, this electron actually absorbs this energy, and then it goes up in the higher energy level, and this is known as the absorption. And the next thing is the stimulated uh, emission. So what is stimulated emission? So when this electron, it absorbs the energy and move up in the higher energy level, and when this absorption is happening at a very large rate, and when some of this electron that is in the higher energy state, it moves down to its lower energy state, and when it loses energy, it releases some photon, because it have to lose the energy, and this uh, like in this photon that is being released get absorbed by this already high energy electron, and when this high energy electron absorb this extra photon, it has twice the amount of energy, so it becomes unstable, and then it goes down to its low energy state, and when it goes down, it releases to another photon, and this to another photon again gets absorbed by this high energy electrons, and this high energy electron continues the same process and releases four other photon, and this is known as the stimulated emission. And then we have the simple spontaneous emission, that is after the absorption, after the electron absorbs the packet of energy, that is the photon, it likes to move down to its stable energy state, that is at the lower energy state. So when it moves from the high energy state to the lower energy state, it emits all this photon, and this is known as the spontaneous emission. And also we have the absorption spectroscopy. So uh, so from, so from the Beer's law. So now we are going to discuss about the Beer's law. So Beer's law relates the amount of light absorbed by a sample to the concentration of the absorbing species. And this absorbance spectroscopy is a method that uses the wavelength dependent absorption characteristic of material to identify and quantify specific substances. So according to the Beer's law, the absorbance that is represented by A, it is equal to log of P naught by P. So what is this P naught and P? Well, P naught is the intensity, or no, it is actually the power of the light that is normal, that is incident onto a sample, while P is the power of that incident light that gets transmitted onto, like, that gets transmitted through the medium, that is the power of the light that passes through the medium. And this Beer's law, uh, and 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 also according to this Beer's law, this absorbance, it is equal to epsilon bc, where epsilon is the molar absorbivity, where b is the path length or the thickness of the medium in centimeter, where c is the concentration. Now let's get into laser. So what is a laser? Well, a laser is a device that emits light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. So in a laser, what are the various components? Well, in a laser we have multiple components. They are the gain medium, laser pumping, the reflectors, the output coupler, and the laser beam. So the basic working principle is such that when the energy is either electrically or optically pumped into the gain medium, so in the figure it is the green part. So when it is being pumped onto it, the electron, it moves to a higher energy state, and when the electron moves to a higher energy state, and it has to come down. So and when it comes down to a lower energy state, it gives out the photon, and this photon that is emitted is reflected back and forth between the two mirrors, which is the which in the figure it is the gray part. So when it moves sideways, from gets reflected up and down, so it creates stimulated emission. So and either one of this mirror will have like a 5% transmittance, so like 5% of the photon being generated can pass through it, and that becomes the output laser. And but in order to know know it more further, let's go into three-stage laser, and then we'll move it into four-stage laser. So now let's discuss three-stage laser. So in a laser we will have either optical pumping or electrical pumping. So energy will be pumped into the gain medium. So the electrons that are in the gain medium, they will gain the energy and they will move up high in the energy level. So in this figure, let's assume that they are moving from E1 or the ground state energy state to the E4 energy state. So when they move upward from E1 to E4, they are not quite stable. So when they reach this E4 energy state, they will lose the energy in the form of non-radiative manner, that is in the form of heat, and they will oscillate downwards to this E3 energy state, also known as the metastable level. And then this pumping will not be stopping, so the electrons in the ground state keeps on moving from E1 to E4, and then from E4 to E3, and it will keep on accumulating because the E3 is stable. So E3 also called it the metastable level, and it is quite very stable. And also it is very common for these electrons in the metastable, in every electron in the higher energy state, to go to the ground state through spontaneous emission. And this so knowing this in concept, we will also be we should also take this into consideration, that that in the E3 energy state there is a population inversion. That is, the electrons in the ground all the electrons in the ground state will have moved from E1 to E4, and then from E4 to E3. So there is an increased population of electron in E3 as compared to E1 and E4. So that concept is also known as the population inversion. And when this spontaneous emission happens by the electrons in the metastable level, they emit out photons. So when they emit out photon, this photon emitted actually get absorbed by another electron in the metastable level. But this electron in the metastable level, they are already in high energy state. So when they absorb this energy of the photon, they become unstable system. So when they become unstable, they goes down to the ground state and release the energy. But they already have this extra energy and they have absorbed another photon. So when they move downward, they release two photons, and these two photons also gets absorbed by another two electrons in the metastable level, and as a result it releases four photons, and this four photon gets absorbed and then it releases eight photons. So it keeps on cascading, so there is an exponential increase in the number of photons being generated. So this is how a three-stage laser works. And if we look at the first diagram, so in the gain medium, all of this cascading photon release will be happening, and at the same, and also along with that, the photon that goes out of the gain medium, it gets reflected back towards the gain medium when it when it gets reflected back from the mirror. And when it gets reflected from the mirror, it passes to the gain medium, and it provides the stimulated emission. And also when it goes through the other end, it was reflected back by another mirror, and so the stimulated, so these two mirror reflects the photons back and forth, resulting in an increased stimulated emission. And one of this mirror will actually have like 5 to 2%, 5, either 5%, 3%, or 2% transmitted. So around 5% of these photo will escape through, and that 5% is what we normally observe as laser. And the first and an example of the three-stage laser is the Ruby laser, which is actually the first laser ever created. And then we'll have the four-level laser. So this four-level laser is quite similar to the three-stage laser. So how does it work? Well, it kind of works similar to the three-stage laser. So the electrons will be pumped from E1 energy level to E4 energy level. So when it moves from E1 to E4, they are not very stable, so they transition downwards to E3. And after they move from E3, there will be population inversion happening in E3, and then again they will move, and they will have stimulated emission from E3 to E2. But when they reach this E2, so they will have stimulated emission. But after the stimulated so during the stimulated emission, they will not go from E3 to E1, but instead they will go from E3 to another state, E2. So the electron, they will move down to E2, and then from E2 energy state they will lose the energy in the form of heat, and then they will go to E1. And also there's another concept of why we can't have two level laser. Well, we can't have a two stage laser because we can't achieve population inversion in such a scenario. So let's get into the concept of fluorescence and phosphorescence. So what is fluorescence? So in fluorescence, what happens is that the material, it absorbs the light, and after it absorbs the light, it gives out the photons or the electromagnetic radiation immediately. Well, but in case of phosphorescence, what it does is that it absorbs the energy and it holds it for some while, and then after some time it release the energy in the form of photon or electromagnetic radiation after some time. So and also the key difference between fluorescence and phosphorescence is that in fluorescence, the emission of light, the emission of light itself, it stops suddenly when the source of the light is removed. So we have a material, and then we shine some radiations like UV radiation or any light onto it, and then and once we remove it, the fluorescence will stop immediately. But in the case of phosphorescence, it is not the case. After the source is removed, after the source is immediately removed, the material will still continue to give out light after even after the source is removed, and it will continue after for few seconds, and then it can go up to more time, maybe a minute, depending upon what type of phosphorescence that we are discussing. And then now let's get into photodetectors. So what are photodetectors? Well, a photodetector is a device that measures photon flux or optical power by converting the energy of the absorbed photon into a measurable form. So this is a very simple definition.
So and then we have another type of photodetector. So we have this also known as a thermal photodetector. So what does this thermal photodetector does? Well, will have a material, and then it is going to absorb the light energy, and when it absorbs the light energy, the material is going to convert that photon energy into heat, and in such cases it is also known as the thermal photodetectors. And then we can like infrared scanning, and we can scan the material using infrared scan to examine it, and that is how we are using it in the medical technology itself. And then let's go into the so photodetectors are usually of two types. One is the external photodetectors, and one is the internal photodetector. So what is an external photodetector? So we have this concept of the valence band and the conduction band. So when the, so when this material when any material absorbs the energy, it excites the electron from the valence band to the conduction band. But in case of external photo effect, the energy that is absorbed, it bounces, it gives so much energy to the electron in the conduction band, not in the valence band, in the conduction band, that it jumps out of the material. So when the electron moves out of the material itself, then that type and if we use this concept in detector, and this are known as the external photodetector. And one of the example of external photodetector is the phototubes, or the vacuum photodiodes or phototubes. So in this case, we have this setup where we have a glass tube, and then we have the two electrodes, and when we apply electric field onto it, nothing happens. But when we shine light onto it, then this material, or the electrons in the in the cathode, it absorbs this incoming light, and then it excites, and then it moves out of the material, and then it goes towards the anode, completing a circuit, and then current starts flowing in the setup. So these are also known as the photodiodes or the phototubes, and we also have the cascading phototubes. And then now let's move on to the internal photodiodes. So what are internal photodetectors? Well, in internal photodetectors, when the material absorbs the photon, the electrons the electron absorbs the photon, and it moves from the valence band to the conduction band. So in the valence band, they don't take part in any form of electrical in conduction or any of that. So in valence one, they just revolve around the nuclei. But when this electron move from the valence band to the conduction band, they actually becomes free to move around, and then it contribute to the conductivity of the material. So this is what we use. These are known as internal photo detectors or photodiodes. And now let's move into the photoconductivity. So what is photoconductivity? So in the concept of photoconductivity, let's take an for example, let's take an intrinsic photoconductor, an intrinsic semiconductor. So when we have this intrinsic semiconductor, and then light, and let's assume that light falls onto it. So when light falls onto it, the atoms of the intrinsic semiconductor, they will excite the electron, and at the same time they will release hole. So this excited electron will increase the conductivity of the material. So when we have this material, and then the conductivity changes, then the potential drop across the semiconductor when a constant voltage is applied across it. Then from that we can actually detect if there's any if there is any light that falls onto it or not. So using this concept, we have the photo conductors, which are actually used as photo detectors. And then we have the photodiodes. So in photodiodes, how it actually works is that we have two types: the PN photodiode or the PIN photodiode. That is uh, there is the p type, and then the n type, sandwich together. And then we have for the pin, it is the p type and a intrinsic semiconductor in between the p type and the n types sandwiched together. So let's talk about the pn photodiode.
So in a PN photodiode, we have the intrinsic semiconductor that in which the majority carrier is host, and then we have the semiconductor that in which the majority carrier is electron, and then these two semiconductors are sandwiched together. And when they are sandwiched together, the electrons and the holes in the border, or in the sandwich region, they actually move from one side to another, leaving only the immobile charge carriers in between. So this sets up a region also known as the depletion region, and they are so-called depletion region because there is no mobile charge carrier, and also the presence of the immobile charge carriers it sets up, and so this immobile charge carrier set up this electric field in which the electron can't pass right through it. So in such a photodiode, when light falls onto it, especially inside the depletion region, there is excitation of electrons and holes. But this electron and holes, they are excited in two separate regions, one in the p side and one in the n side, but they can't cross this depletion region and then recombine because of the immobile charge carrier or the electric field that is already in place. So these charges accumulate in the p type and the n type, and so they and because of the accumulated charge, they generate an EMF. So this EMF, and then where once connected, they will generate a potential difference. So this type of photo detectors are known as photodiodes. And then one we have the avalanche photodiode. So the in the concept of the avalanche photodiode, it is very quite similar. So in this case, what happens is that when light falls onto it, there is an avalanche breakdown that happens inside. So what is avalanche breakdown? So so the electron that is knocked out of its orbit, it moves inside the inside the photodiode. So when it moves inside the diode or the semiconductor material, it knocks out other electrons from other atoms. So after some time, the number of electron accumulates, and also and I explained earlier, this electron it moves and knocks out other electrons from other atoms, and after some time, this number of electron that is being knocked out increases exponentially. So at the output, the amount of electrons, or in the amount of electrons that we get, or the amount of current that we get, increases exponentially, and in such case, it is also known as the avalanche photodiode that utilize the effect of avalanche breakdown. Now let's get into optical amplifier. So the EM doped fiber amplifier, or the EDFA, is a widely deployed technology in optical amplification. And how it works is that we will have two parts. The one will be the signal, and another will be the pump. So let's take an example. So the pump will be light of 90 nanometer. So when this light hits this iridium doped ions, it will excite the electron from the ground state to the higher energy state. And when they move from the ground state to the higher energy state, they are not very stable. So they will lose their energy in a non-radiative manner, and then they will accumulate in the metastable state. So, and when they accumulate in the metastable state, there will be a population inversion. And at this time, if a signal of 15 nanometer, that is a photon of 15 nanometer, comes in contact with this electron in the metastable state, then this high energy electron will absorb this 15 nanometer and become unstable, and then it would transition back to the ground state. So when they transition back to the ground state, they will release two photons of 15 nanometer. So these two photons of 15 nanometer will again get absorbed by the electron in the metastable state, and then and again two of this electron will move down to the ground state and release four 15 nanometer photons, and as a result, it will keep on increasing. So this is a technique that is used for amplification of the 15 nanometer. And in this concept, we have two bands. One is the conventional C band, and one will be the long band. So in the conventional C band, we can amplify wavelength of 1550 nanometer to 1565 nanometer, and for the pump we have to use that 980 nanometer, and we have the long band where we can amplify signal from 1570 nanometer to 1610 nanometer, and the pump should be 1480 nanometer. And then we have the absorbs we have the here we have the absorption and the emission spectrum. So we can see that for the absorption spectrum, it is absorbing from 1550 nanometer, and then 1550 nanometer to 1550 nanometer. And then for the emission, it does not emit at around well, it does not emit around 1450 to 1500 nanometer, but it emits around 1530 to 1550 nanometer. Now let's get into quantum efficiency. So what is quantum efficiency? So when we take a material and then photon hits on the material, so what is the probability that an electron hole pair will be generated? That is when a photon hits on it. So this probability is also known as the quantum efficiency. And then we now will move on to another concept, that is responsivity. So what is our responsibility? Well, responsibility is nothing but the photocurrent that is generated for every incident power. So per unit power. So if we have 1 watt, and then for 1 watt if we generate 1 milliampere of current, then that ratio is also known as the responsivity. And then we'll go into the optical modulators. First we'll have the acousto-optic effect. So what is this? So the refractive index of a medium is changed by the presence of sound. So we know that sound is composed of the compression and refraction as it propagates through. So when we have a medium and then sound hits on it, the atoms inside the medium, it undergoes stress, so they have patterns of compression and refraction, and this pattern causes the refractive index of the medium to change. And this pattern and this like the intensity, no, not the intensity, the graph of the refractive index inside the material, that is along the material, looks like that of a wave. And this wave, and as I've explained, and this wave nature of the changes in the refractive index is due to the compression and refraction of the sound wave. And then let's move on to the electro-optic effect. So what is the electro-optic effect? Well, and as I think I have explained earlier about this electro-optic effect. So when we have a material and then light falls onto it, there are already this electrons, they are already the charge carrier inside the material, and this charge carrier is inside the material, they got aligned by this electric field. And since the light itself possess electric field, so when they interact with these charge carriers inside the material, there is an aligned charge carrier inside the electric field. It causes bending of the light, and this is also what we call as refractive index. So how do we control this refractive index? If it just is about if it is just about aligning the charge carrier in the charge the if it is just about aligning the ions or the electrons inside the material, so when we apply electric field across the material, then the electrons and the charge carrier inside of them, they align, and by controlling how much by controlling the extent of their alignment, we can control the refractive index of the medium. So this is also known as the electro-optic effect. And now now we have the Kerr effect. Well, the Kerr effect is nothing but it kind of states that the refractive in the change in the refractive index is proportional to the square of the applied electric field. And then we have the Pockels effect, which says that the change in the refractive index is proportional to the applied electric field. So there is not much of a difference. And with this we'll end the brief summary about the introduction to photons.